Okay, if you're still with me, let's talk about Carnot's theorem. Carnot's theorem states that the efficiency of a heat engine is dependent on the temperature of the hot reservoir and the temperature of the cold reservoir. Nothing else matters. Doesn't matter what kind of engine we have. It doesn't matter what the cylinder size is or the length of the stroke or anything else. Two things only: the temperature of the hot reservoir and the temperature of the cold reservoir. And Carnot's theorem is stated like so. Temperature hot minus temperature cold divided by temperature hot equals efficiency. This theorem enabled people to answer a question that had been floating around in engine building and locomotive design for a few years. And that question was, why do high pressure engines work so much more efficiently than low pressure engines? And the answer obviously now is that by increasing the pressure of the steam, we increase the temperature of the steam. Essentially, we are increasing the temperature of the hot reservoir, and that gives us a bigger temperature differential to take advantage of. Although locomotives worked by having valves letting steam into and out of the cylinders, locomotive designers immediately fell onto Carnot's theorem to help explain the efficiency of a steam locomotive. So, even though Carnot's theorem applied to a closed system, they still took the high temperature reservoir as the temperature of the steam in the boiler and the low temperature reservoir as the temperature of the air to which the steam is being exhausted, and they calculated the theoretical maximum efficiency of a steam locomotive. Okay. So let's think about a steam locomotive. The steam is at about 100 degrees centigrade. The temperature of the atmosphere is about 25 degrees centigrade. So we plug these three numbers into the Carnot theorem. Oh, wait a minute. Sorry about that. We plug these three numbers into the Carnot theorem, and we get a theoretical maximum efficiency of a steam locomotive at around 75%. The actual thermal efficiency of a steam locomotive is rarely over 10% and can be as low as 2%. So this number really did not reflect reality, and Carnot was a little bit troubled by this. He was wondering if perhaps he had to incorporate some sort of correction factor into his theorem or into this equation to account for what was going on in the real world or among real locomotives. Turned out that if we take the temperature not in degrees centigrade or not in degrees Fahrenheit, but in degrees Kelvin or on the absolute temperature scale, we get a thermal efficiency of a steam locomotive somewhere around 20%, which is much closer to reality. Much of the Carnot's numbers did not make a lot of sense to engine builders. The theoretical maximum efficiency was way too high in many cases, but with the introduction of the absolute temperature scale, we were able to much more accurately predict the efficiency of a heat engine. So that's why when you see Carnot's theorem written, it always has capital T or degrees Kelvin or the absolute temperature scale. It also allows you to think about theoretically 100% efficient steam engines. If we have 0 degrees on the absolute temperature scale and a hot reservoir at any other degree above 0, then temperature hot minus 0 divided by temperature hot equals 100%. Obviously, that's not going to happen. So we can think about the difference between the hot reservoir and the cold reservoir above absolute zero in thinking about the efficiency of a heat engine. Our final video will talk about the concept of entropy and what the implications of entropy were for the scientists in the 1800s and the engine builders who were thinking about steam engines and work and power.